Hello and welcome to another session of molecular orbital theory. This time we are applying the molecular orbital theory for naphthalene. In earlier cases, we have described it for cyclopropanyl and butadiene systems. As far as the carbocyclic systems are concerned, we had a discussion on for benzene molecule, and this time we are going to discuss about the case of naphthalene. We understand that the naphthalene has a flat structure with the 10 carbon atoms and the 10 pi electrons that have been depicted as shown in the figure, and they have been numbered also 1, 2, 3 and all that. The 9th and 10th carbon are those which are the connecting situations there, and the z-axis and y-axis and x-axis have also been demonstrated. If you look for the overall symmetry of the molecule, this has a structure resembling to ethene, that's C2H4. So I mean to say that it has a D2H symmetry. Now, working with D2S symmetry, we need to take care of the reducible representations for the pi orbitals as the basis. This is the D2H character table at your perusal, and let us try to get what we call as the characters for the reducible representation. And to get it done, what we'll do is we'll assume that if the atom for pi orbital is shifted, it will contribute to +1 for unshifted, and if it gets shifted, it gets the contribution to -1, while if there is no change at all, then it will be contributing 0 for that particular representation. So we have the D2H symmetry. We have identity C2 along y-axis, C2 along x-axis as demonstrated center of inversion, sigma xy, sigma xz, sigma yz. So these many are the symmetry properties of this molecule. We know that there are 10 pi electrons, and because the identity does not do anything, it has to have a contribution of 10. As far as the C2 along the z-axis is concerned, if we'll do the rotation by 180 degree from the z-axis, as you can see in the figure, all the atoms would get shifted and therefore contribution would obviously 0. When you talk about y-axis, you can see that the y-axis is passing through between the two atoms 9th and 10th. So even if you rotate along the y-axis, what would happen is that 9th and 10th pi orbital would be completely inverted, while the rest of the element would be completely shifted. So the contribution would fall to -2. Along the x-axis, you can see if you do it, all the pi orbitals would be shifted. Of course, the same is true for center of symmetry. And if you talk about the xy plane, talking about xy plane, which is a flat molecular plane, all pi orbitals are getting reversed. So you have -10. And if you talk about xz plane, it contributes to 0. And if you talk about yz plane, similarly, it would contribute to 2, of course. So the reducible representation that we have obtained for pi orbitals of naphthalene are the values that we have just now seen. That is 10, 0, -2, 0, 0, -10, 0, and 2. The next job is to, of course, decompose into irreducible components and use the standard reduction formula that we have described in many cases earlier. And when you do so, you'll find that the respective irreducible components would come in your representation by the sense that has been displayed on the board. So you find that B2G has appeared twice, B3G thrice, AU twice, while B1U has appeared thrice, and B2U does not contribute anything, and B3U also does not contribute anything. So we see that contribution from the 4 irreducible representations are observed: 2 from B2G, 3 from B3G, 2 from AU, and 3 from B1U. So these are the representations that we have obtained by taking pi orbital as the basis. Now, if we develop the SALK equation and use the concept of SALK, what would be the most important thing is then 2p z orbitals form the 3 subsets. Subset 1, that is something like phi 1, phi 2, phi 5, and phi 6. Subset 2, phi 2, phi 3, phi 6, and phi 7. Subset 3, phi 9, and phi 10. So these are the equivalent orbitals, and in constructing the SALK, we have taken that particular idea, and using the projection operation technique, we have been able to develop the equations which are now on the board for B2G symmetry, that is psi 1, and this is the second one is psi 2 minus phi 6 minus phi 7 plus phi 3. Normalized wave functions are for the third one is phi 1, phi 5, phi 8 and phi 4 with the positive and negative signs coming alternatively. For psi 4, this contribution is coming from everywhere, not only from B to G. So you have psi 2 minus psi 6 plus psi 7 minus psi 3 and so on. So you have actually developed 10 equations that can be obtained using the projection operation technique. Had you not been using this technique, what you are left with the idea that you construct a determinant of order 10 by 10 and then you need to solve it. But construction and manipulating mathematically such a big determinant is of course a trouble. This is a group theory which allows you to make it simplified, and therefore using this concept, the 10 by 10 matrix would be decomposed into B2G symmetry that would result in 2 solutions of energy, B3 symmetry that would result in 3 solutions of energy, AU would result in 2 solutions of energy, and B3U again would result into 3 solutions of chemistry. So we have altogether now 2 plus 3 plus 2 plus 3, that makes it 10 solutions of energy. And looking forward to how do we compute the cases? How do we calculate the workout? So if you make some equations on the Hückel's treatment, we earlier know that for all those integrals of the type where phi I, h phi j, d tau, they are equal to alpha, if we say I is equal to j, and otherwise if they are beta, if simply I is not equal to j, but they are interacting orbitals or atoms, and it's 0 simply if I and j are non-neighboring atoms, they are not interacting orbitals or atoms also. So this is kind of the selection rule that we have been using. And once if you are interested in finding out the value of h11, that is psi 1 h psi 1 d tau, now you have developed the equation. That's psi 1 is equal to actually phi 1 minus phi 5 minus phi 8 plus phi 4 and so on. So when it is normalized comes, the square 1 by root 2 and 1 by root 2, that will make 1 by root 4, and 1 by root 4 would make it 1 by 4 outside on the table. And once you solve the components and just put the appropriate things common, of course the 1 by 4 is also there. And when you do it, you need to have a large number of solutions. But then what you are supposed to do is simply apply the Hückel's treatment or Hückel's molecular orbitals. So for all interacting orbitals and non-interacting orbitals substituting value beta or 0, what you have is 1 by 4 plus 4 alpha, that is nothing but the alpha. So H11 is alpha in this case, H12 comes out to beta, H12 and 21 they are same, and therefore H22 in terms of the energy has the value of alpha plus beta. So the attitude, the secular determinants comes out to, for the 2 by 2 order determinant, you have alpha minus E beta and alpha plus beta minus E, and if you solve these values for the energy, you get some simple equations that give certain solutions. For this, there are two roots with x equal to minus 1.618 and x2 is equal to 0.618 have been obtained, and because alpha minus E upon beta is equal to x, we have two solutions of energy corresponding to alpha plus 1.618 beta and alpha minus 0.618 beta. So we have two solutions of energy. Now, in a similar manner, you can proceed for another equations as well. But if you want to find out the coefficients also, then you can go with secular values, secular equations. Now they are quite simplified instead of having a 10 by 10 kind of equation or 10 odd equation. So what we do is we just substitute the value of h11, h22, etc. that we have determined here. Once we do it, we are able to get the values of C1 and C2 and normalization constant, etc. And that ultimately gives you something like this, which gives C1 comes out to be 0.526 in this particular case. Similarly, you can proceed for the another functions as well. And if you do it, the other equation is 0.526 and 0.850 C1 and C2 values respectively, and get them normalized and do all kind of manipulations that you can do here. And once you do it, you get the equations of the type, and similarly for the negative value and positive value also, you get the equations of the type. So the normalized equations with their constants, we are able to calculate actually without developing much of mathematics and making it simpler. Once we do it, we have certain set of equations again here also. These equations are very useful in drawing the molecular orbital diagram of this particular molecule. As far as the remaining systems are concerned, you have the energy for E3, E4, E5, and systems have been displayed. Alpha plus 1.303 beta, alpha minus beta for E4, alpha minus 2.303 beta for E5, and the respective equations with their coefficients have been displayed. Similarly, you have E6 and E6 comes out to be alpha plus 0.168 beta, and similarly E7 is alpha minus 1.618 beta. For other symmetries, E8 drops out to be alpha plus 2.303 beta, and the rest of the things are like this. E9 is simply alpha plus beta, and E10, that is the last equation, is alpha minus 1.303 beta. So these are the values that we have calculated without actually doing a huge mathematics that would have otherwise been involved. Now the things are simpler. The next thing is simply to draw the molecular orbital diagram. And if you wish to find out the resonance energy also, you can do it. In terms of the scale of beta, alpha plus 2.303 beta is the B1U symmetry correspondingly. And as you proceed forward, you have alpha plus 1.618 beta, alpha plus 1.303 beta, alpha plus beta, alpha plus 0.61 beta. They are all corresponding to the bonding molecular orbitals, whereas alpha minus of 0.61 beta, that is they are the values which will correspond to the antibonding molecular orbitals in terms of the units of beta. That's all for now. This is how you can simplify the calculations for naphthalene molecule. Thanks for watching.